let's pick up with the same two independent Brownian motions that we left off with from last time. So in the previous clip we used the running maxima, which were both increasing in each coordinate, to look at the distance of the shortest distance of the bug from an area where there's grass. And here I'm going to use x and y to just track the position of a bug on some table, so there's no grass in sight, and it's not moving in any kind of one direction in particular. So I'm just going to use the Brownian motions to denote its coordinates. Xt and yt are the coordinates of the bug, and it's a table. So we're thinking of a circular disk of radius r, and what's going to happen is that as soon as the bug and here it's sort of started out there and ended up here, as soon as that bug reaches the edge of the table, it says flies off. And so we can model this with a hitting time. So tau is the first time that r of t, so this is the radius, or I guess this would be the distance from the origin of the bug, this distance right here. The first time this distance reaches the level r, which is the radius of the table, that's when the bug flies off. So this is the way we define this random hitting time, and we're out to compute its expected value. So we're looking to compute the expected value of tau the first time the bug flies away. Let me mention something on this issue of polar coordinates. So depending on the geometry that you have, you kind of work with different coordinates at times. And so kind of motivated by this original example, you could look at the very first time that this Brownian particle leaves the edge of of one of these of the box, one of the edges of it. So a similar problem but a different geometry. Here we're kind of forced to work with polar coordinates because we have a circular geometry on our hands. So let me mention a little bit about this in case this is the first time you're seeing this. So a point that has Cartesian coordinates x and y can always be described by a radius, a distance from the origin, and an angle away from, usually measured away from the x-axis, and that angle is denoted by theta. So you can either know r and theta, that's polar coordinates, or you can know x and y, which are Cartesian coordinates. And to translate between the two is fairly easy. If you just think of this triangle here and you have the polar coordinates r and theta, then the projection of this vector down, or the length of the side of this triangle here, would be r cosine theta, and that's just your x coordinate. And then projecting this vector onto the y-axis gives you the length of this side of the triangle, and that's r times sine theta, and that's your y coordinate. So once you make this transformation, we're not going to have to do integrals here, but in general, if you have to now integrate in this new coordinate system, you want to know, you can't just replace the dxy, the dx and the dy by the dr and the d theta. To be careful. So here's kind of one way to think about this. When integrating in Cartesian coordinates, you're adding up units of kind of area that's described by these little boxes. So you have a little square of side, infinitesimal side dx and infinitesimal side dy, and their product is giving you kind of the area that you're adding up, that you're integrating over. In polar coordinates, just the way the geometry stacks up and concentrates at the origin, you have these little slices that you will add up. And so the slice has a length dr. This is the length of the slice here, and this arc length would be given by r d theta. So the further you get away from the origin, the larger r is, the larger the slice is, which explains this scaling by r here. So the area in polar coordinates is r dr d theta, whereas in Cartesian coordinates it's just dx dy. So I think, just to mention the use of polar coordinates here, you can kind of get a glimpse of the fact that this theta t, which is the random angle where the bug is probably going to have a uniform distribution. So the bug has no preference as to where to go, and neither do the Brownian motions. That's the reason for it. And so most of the the important part of the distribution, the dependence on time, for example, is stuck in the this distance from the origin, r. So what else is there to mention? I think let me just talk about martingales and how we compute the expected time that the bug flies away. So this type of problem would be very difficult to do, from basic principles, and any kind of integration would be kind of tough to carry out anyway. But there's a standard approach for all this, and let me just kind of show you how it works and discuss how it could work in general. So remember what martingales are. Here's the definition. Martingale M is integrable, and it has to satisfy this more important property that the best predictor of a future value, expected future value, is the current value itself. So if it's a Markov process, you would condition on just m at time s, and if not, just condition on the whole path at time s and by time s. And so what do we remember from martingales? We remember that Brownian motions are martingales. The Brownian motion squared was not; it was increasing, and so counteracting it by a linear term here, reduced this process to be a martingale. And so we shown this already, so I'm not going to cover those steps. But it would also be fairly easy to see that the sum of two martingales, which is what I've defined here, m of t is equal to rt squared minus 2t, is again a martingale. That's just follows from the linearity of expectation. If you had two terms in the sum, the expectation would slide through, and you would apply the martingale property to the individual terms, which are this one and this one. And so clearly this r squared comes from the x and the y squared, and this 2t comes from the two linear t terms. And so let's see how to use this. The key to using this is what's called the optional stopping theorem. The name comes from the fact that the idea, I guess, is that when we get to the edge of this boundary, the bug flies off and we stop observing the process. So the process is stopped, in other words, there. And what the theorem tells you is that the martingale property will hold not just for deterministic times, little t and little s. It will hold for bounded hitting times. So here I'm using capital letters to remind you that these are random times, s and t. And what this is saying is that you can plug them into this definition and still have that definition hold, with the caveat that they're bounded. And this can be sort of relaxed in a number of ways, and what I would suggest is often just kind of ignoring that part and plugging it in and see what kind of answer you get, and then worrying about the repercussions sort of later. So let me just work that through, and then I'll give you a word of caution and an idea of how to fix this issue with the times being bounded. So, and one thing you do want to convince yourself of is that this tau is by no means a bounded random variable. It can take fairly large values, and so it's not bounded above by a constant. In any case, I'm going to be replacing my s with a 0, which is a random time. Not random, but it's a time. It's bounded, so that's good. And the t, I'm going to make this hitting time tau the first time the bug flies off. And so evaluating the m at tau gives me this equation here. M of 0 is 0. The origin, distance from the origin at 0 is 0, and 2t at 0 is certainly 0. So I immediately get this equation, and this conditioning goes away as well, because conditioning on 0 doesn't help me. And so you can kind of see that I very quickly get this formula out. What is the value of the distance from the origin at the time at which the distance from the origin is little r? Well, it's just little r. So this is by definition of the hitting time. I have this equality here, and that leads my first term to just be the r squared over 2. That's what this term reduces to, or I guess it reduces to just r squared. And then I have minus 2t from this term, or I guess 2 tau. So use the linearity of expectation, divide by 2, and you very quickly arrive at an answer that would have been very tough to get with other methods. So so where does that leave us? So I would suggest, when working, you have a similar problem like this on your homework, and let me just make a couple of remarks as to why this worked so well here. The stopping time should really involves the process R, and we wanted to compute the expectation, which is just a linear function of time, or I guess it's time appears linearly, in other words. And so this martingale in particular, was kind of crafted or selected based on those two demands. We needed the process R, which is going to be evaluated at the hitting time to make it easy to evaluate. We know what the value of R at tau is, it's little r. And the second requirement was that it had a linear term in time so that we could get out an expectation of tau. And you can kind of think, if you wanted the second moment of tau, or the variance, you would need a martingale that had a t squared somewhere. And so a similar thing would apply if you wanted the moment generating function of tau. Then you would need some this t to appear in the exponent of some exponential e to the something t. And so you design these martingales in order to help you kind of evaluate expectations like this. And let me leave you with I guess it's not a word of caution, this is more of a way to fix this issue around bounded hitting times. The idea is to maybe not use tau, it's not bounded, but let's take the minimum of it in any finite time t. So take minimum of tau and t, where t is just some finite constant. And now this is clearly bounded. The minimum of these two is less than or equal to either, so it's bounded by t, and therefore this identity would hold with just tau replaced by this minimum here. And so what I would get out of this formula is one side would be the expected value of minimum of tau and t. That would correspond to kind of this side of the equation. And the other side would not give me the nice simple expression as here, but it would give me r squared, the minimum of tau and t, divided by 2. And then what I would need to do is take t to infinity, which again must be done fairly carefully. Maybe I'll mention more about this in the next lecture, but the basic theorem involved here is called dominated convergence, which basically tells you that if you have something random here that depends on some t, and you can bound it above by something that has a finite expectation and doesn't depend on t, which would be, for example, tau, the minimum of t and tau is bounded above by tau, which is a good exercise to show that this has a finite expected value. The other side, right, how would we bound this by something that has a finite expectation and doesn't depend on t? Well, it's bounded above by r squared. This is the distance from the origin before the bug flies off. And before the bug flies off, it's always trapped in this disk, and therefore bounded above by r squared. And so taking t in this case to infinity, you're justified in exchanging a limit and the expectation of both sides, arriving us again here. So I guess that would wrap up this calculation. You get some practice with something similar on your homework.